Thank you, Barry, for the introduction. So I will be talking about an attack we developed for, well, SCARF. And this is the result of a work we started at the Lawrence workshop last year in Leiden. I met a bunch of people there. I'm not going to name all of them, but yeah. So before I start talking about the attack we did for SCARF, I first want to give some context around SCARF, because SCARF is a very unique tweakable block cipher that has been specifically designed for what's called cache randomization. So, well, we all know probably about these cache attacks, which allow us to extract information about the memory addresses that some user uses or some program uses. And so the way that these attacks often work is we try to fill up a cache, and then we just check which addresses are no longer in this cache. And for us to be able to do this, we kind of have to understand how this cache works. So when we want to access an address, we just take part of this address, like 10 bits, depending on the size of the cache. We then look in the corresponding row in this cache, and then we check the rest of the address to see if it's actually in there, and if it is, we can access the data, and otherwise we are evicted. The data has been evicted, and we have to go to a higher level in the memory hierarchy. And so if this cache is shared, we can basically derive information. But the way we do this, we have to somehow have knowledge about this index, so we know, so we can get information about the user and information about these collisions. So a while back, scatter cache has been proposed, where the idea is to randomize this index based on the tag and some tweakable block cipher. And so because the user doesn't know or the attacker doesn't know the key of this block cipher, it becomes really hard to actually know whether two things collided or will collide. And then at USENIX 2023, SCARF was proposed as a block cipher that is specifically designed for this context. So it has a 10-bit data path, a 48-bit tweak, and then a really long 240-bit key. And it has some, because it has some really strict latency requirements, because it has to work in this cache environment, they actually decided to invent some new attacker models instead of the usual models for tweakable block ciphers. And so the model they started with was this collision model. Because basically the only thing you can observe in this cache setting is whether two addresses collide in the cache or not. So in this model, you can basically query a pair of plain text tweak pairs and then see whether the output collides or not. And so the idea of this model is that you won't be able to distinguish SCARF from this setup instantiated with a random tweakable permutation. But in their opinion, this is kind of hard to analyze. So they decided to invent a second model which kind of uses information about these collisions. So if we know that these two things collide, then this value in the middle is the same. So we can basically start building a block cipher or a tweakable block cipher from an encryption with one tweak and then a decryption with a second tweak. And so their idea behind this is that if you design the tweaky schedule well enough, then basically for every round you design, you get 2 rounds of security, so you can significantly reduce the latency. And so most cryptanalysis, especially the one in the design paper, as well as other public cryptanalysis, has always been in this encryption-decryption model. But for this work, we have focused on the collision model because in a way it's significantly simpler because we circumvent the fact that we need to attack twice as many rounds. And so, okay, you can also go back to the first model, which I will discuss later because we use this in the attack. And so their security parameters are that in either of these models, you can't distinguish with less than 2 to the 40 data and 2 to the 80 time. So what does SCARF look like? Well, so this is a round function of SCARF. It's a 5-cell network where each branch is 5 bits. And to squeeze as much key material as possible in this round function, they actually, so they add a bit of key to one of the branches, but then all the rest of the round key is just multiplied with one of the branches with a big matrix multiplication. So this introduces a lot of kind of non-linearity compared to the key, but this is also just a linear operation otherwise on the data. And then there is this S-box and this other function G, which are not really important for the analysis in this work, but which are also evaluated. To generate these round keys, a tweak key schedule is used, which mixes the very large key with the tweak. But it's a bit unusual, so it looks basically like a substitution permutation network, where the 48-bit tweak is expanded by adding some zeros in there, and this to a full 60 bits, and then they add a key, and then basically they already immediately extract the round keys for the first two rounds, which I have given here in color. So the black color corresponds to this key here, and then the others are just in this matrix. They use this very dense linear layer, which is basically the sum of 7 rotations. The exact details are not really important for this presentation. They have this bit permutation here, and then another linear layer with S-boxes in between. So for our attack, as I said, we wanted to do this in the collision model. And our idea for this is that we want to start with basically 2 different tweaks, but the plain text is the same. And then we might be able to, through each round, keep this collision between the 2 plain texts. So to do this, we analyze the round function through differential cryptanalysis. So what I've written down here in black is basically just the value of the input. And then in red is the difference between this input and the second input. And so if we start with 2 zeros, then we get a bunch of zeros everywhere. But if we want a 0 in the output, then if we trace back from here, then we see that we need a 0 difference on the S-box, which means a 0 input difference on the S-box, which we can only guarantee if the difference on this round key, which is introduced by the use of 2 different tweaks, is actually 0. And then for the other side, we can also trace this back. So we basically need a 0 difference out of this kind of function in the middle, which is guaranteed over G, but not over this matrix, because this matrix is also made up of tweak key, out of the tweak key. So there is a difference on this. And here we know that the difference is basically the product between this state and the difference on the matrix. And so our difference is guaranteed as long as this left branch lies in the kernel of the difference of the matrix. Yeah. But so to be able to accomplish this, we need to find some kind of difference on the tweaks that guarantees in the tweak key path that we kind of have these conditions. So what I have here is basically a truncated differential on the last part of the tweak key schedule. So we get the S-box layer, the linear function, which I have spread out a bit here to make clear where everything goes, and then the last S-box layer. And so the idea here is that if we have an input, like if the tweak is already just added here, then if we have a difference on the second and the third bit of the first S-box, we can, with pretty high probability, guarantee that these black parts here have a 0 difference, which corresponds to this delta. And so what has to happen for this to work is that the first and the last bit of this S-box have a 0 difference, which happens with a probability 5 in 16. And then otherwise, we basically get almost random matrices in between. So we can then look at the data path and see with what kind of probabilities these collisions will propagate. So we use the distribution of the differences to actually compute these probabilities. So for the first round, this is around 2 in 5, which is to the minus 1.3. The second round is trivial because there's no difference on the matrix. And then the last two behave almost as random matrices, which gives us around 2 to the minus 4. Multiplying everything together, which implies some independence assumption, gives us an estimated probability of 2 to the minus 10 plus 2 to the minus 11 for a collision. In this case, we also assume that if this specific kind of difference path is not followed, then we still have a random 2 to the minus 10 probability of collision. And in reality, we actually observe something significantly better of 2 to the minus 10 plus 2 to the minus 10.5. And this is, we assume, the result of basically a very simplistic analysis of the data path. In the paper itself, we actually extend this, and we find a 6-round distinguisher on the first 6 round of SCARF with around 2 to the 30 data. And this is the first proper analysis of SCARF in this collision model. But what I promised, an actual attack on full SCARF, that's the title of this paper. And so what we wanted to do is we tried to extend this 4-round distinguisher to a key recovery attack. And the idea behind a simple key recovery attack for this isn't too difficult. So what we basically have to guess the initial parts of the key so that we can guarantee after, so this is the first part of the key, a tweaky schedule, so that we can guarantee this difference here. To do this, we actually have to guess the full first round key, which also allows us to immediately skip 2 of the 8 data rounds. And then we have to guess an additional 10 bits of the second key. And we then know the difference here, so we can kind of construct inputs here that collide after this round and also after the last round. But if we do this, we basically have to guess the key, then formulate a possible pair of tweaks that will guarantee this input difference here and this correct input difference here, and then evaluate this. So that means that the data we use actually scales with the number of keys that we have to guess. So naively, this means we need at least 2 to the 70 data, which is significantly more than what we have available according to security parameters. So what we want to do is actually be able to reuse as much of this data as possible. But it's not immediately clear how we can do this. So what we suggest is that instead of working directly in the collision model, we actually simulate the collision model using the encryption-decryption model. So as I alluded to before, you can actually simulate this. And what we do to simulate the collision model is we do 2 queries in the encryption-decryption model. With both of them, this tweak T2 becomes some constant tweak. It doesn't really matter. And then we evaluate with the first tweak and the first input and the second tweak and the second input. And so if these collide, then we can actually peel back this function because it's the same. So these two actually had to collide. And so we can use this to just evaluate a set of suggested tweak plaintext pairs and then evaluate all the possible collisions between all the kind of 2 elements in this set. And for that, we only need the size of the set number of queries, so we get a quadratic speedup or quadratic improvement in data. Now then the second challenge for this becomes how do you choose this input set to guarantee that we stay under the data limit and also have sufficient samples for our property. So the first thing we did is we split up this set into a product of 2 sets, one for the tweaks, and then for each tweak we will evaluate the same plaintext, and we will actually evaluate all the plaintext. So we get the full codebook for each tweak. Because this guarantees at least 2 to the 10 kind of right pairs of samples we can do in the data path. So for every kind of tweak pair we find, we then have at least 2 to the 10 samples. And so now we still have to choose the tweak pairs. And for that, we made 2 decisions. First, the tweaks we sample will be some affine subspace. And then we also split this set up into a product of sets for each kind of S-box. So for each S-box, we make a decision, and together they come together as one large affine subspace. So the reason we do this is, so the affine subspace will become clear later, but the reason we do, we split this up is because then we can, instead of kind of guessing all the key material that is necessary here and allowing all possible differences kind of on this whole like two-round state, we extend our differential characteristic to only allow one specific difference. And the reason we use this difference at the input of the second S-box layer is because if we invert it through the linear layer, then 4 of the S-boxes will have the 0 difference at the output, and that also implies a 0 difference at the input. So for these sets, we can just choose a single constant. And this allows us to significantly reduce the data. And then what is left is that for each of these S-boxes, we have to choose an input set. And this becomes an optimization problem where we want to guarantee for all possible choices of this K1, we have at least a minimum number of right pairs, and then we maximize over that using all the tweaks. This is not an easy optimization problem, but because of this, because we split this up, this becomes significantly easier. And we also want to guarantee that the dimension of the full set is only 29, because multiplied with the number of data pairs we use, we get 2 to the 39 data, which is below the data limit. And so as a result, we basically find that averaged over kind of these guesses of the second round key, we get 2 to the 88, 288 pairs of tweaks that we can use, times 2 to the 10 gives us a large number of samples for our property. Now, an additional novel result that I won't be talking about in this paper is that we also develop a method using quasi-differential trails to evaluate what the minimum number of pairs over all these K2 guesses is. And so to guarantee that there isn't a key for which there might be no pairs at all. And so we evaluate this, and it's basically 248. So we are guaranteed to have sufficient samples independent of whatever key guess we have. Now, with this, our problems are still not solved, because now, naively, the time complexity is too high, and we only have like 34 bits of filtering. So to reduce the time complexity, we use some of the kind of intricacies of the tweaky schedule, mainly the fact that for the data path, we are not interested in what the tweak and the key are, but just the sum between them. And the same for the rest of the tweaky schedule. I mean, the only thing that matters is the sum between the two. So instead of guessing the full 60-bit key here, we actually guess the co-set of our set T that we are in. And because T is a subspace, this reduces the number of guesses to 31 bits, or 2 to the 31 guesses. And then we can basically work with these inputs, so we can quickly solve which inputs are in U and satisfy our characteristic, at least up till here. Then we can get the number of the inputs we need, and that collide after 4 rounds, and then we can basically find all the tweaks that have the same difference as our inputs, and also collide for these pairs. And then for each of these, because we have the tweaks now, we can just solve for the key. We can then also further solve our characteristic to get the rest of the key, and we just add to some counters for every collision that we find. And so what we end up in the end, or what we end up with in the end, is basically all the counters that are sufficiently high correspond to a possible key candidate. And so this whole process, if you also introduce some pre-computed lookup tables, is around 2 to the 76 time, and then uses 2 to the 39 data. And so there was one more problem that I mentioned earlier, and that is that we don't actually have enough data to uniquely identify a single key. And so we have an additional process that allows us to identify this key uniquely. And the way we do this is we actually guess some more key material, so that instead of using a property, evaluate the property that starts at the input of this S-box, the property actually starts at the output of this S-box. So we have to do that, we have to guess an additional 20 bits. Okay, and then we get two more, we get kind of 3 different cases. So if the initial guess and if the initial and the additional guess are both incorrect, this will basically behave as a random permutation, as a random function, so we get a 2 to the minus 10 collision probability. Then if the initial guess was correct, but the additional guess is wrong, then this behaves as our old property. And then if both are correct, then this behaves as a new property. Now, on average, over the extra keys we have to guess, we get around 90 tweak pairs, so 90 times 2 to the 10 samples. This is actually not enough to uniquely find this 90-bit key, but it does suffice to uniquely find this 70-bit key by only trying to distinguish this first and this third case. And so with that, we finally have, like, we can completely find this first round key, and then we can peel back, and then we only have to attack 6 round scarves anymore. And so in the paper, we go into a bit more detail about how you attack 6 round scarf, and then 4 round scarf, and then finally for 2 rounds, you just guess the final key. And so that's it. So in conclusion, we presented 2 new attacks. The first one in the collision model on 6 rounds, and then an attack that breaks the security parameters of scarf in the encryption-decryption model. And additionally, we developed also a novel method for guaranteeing a minimum of write pairs over some input structure. I didn't talk about this in the paper, in the presentation, but it's also interesting in other contexts outside of scarf, whenever you basically use input structures to set up a key recovery attack for differential cryptanalysis. So with that, I thank you for being here. If there are any questions, please ask.